Thank you all for joining my presentation. Today we present Hemiola, a DSL and verification tools that guide design and proof of hardware cache coherence protocols. This is a joint work with Adam Chipala and Arvind, and I'm Junwon Choi from MIT CSAIL. Hardware memory subsystems are extremely complex. A memory subsystem usually consists of hierarchical caches, where L1 caches are the lowest ones, directly communicating with processor cores, and the main memory DRAM as the root. The system receives multiple requests at the same time, and they are handled concurrently. As seen in this figure, we may have a memory request from a core presented in red, and some caches may be involved with this request. At the same time, we may have another request from another core presented in blue, and some other caches may be involved with the blue request. When there are multiple memory requests being handled in a system, what will be the algorithm that makes such concurrent execution correct? A so-called cache-coherence protocol controls the caches and the main memory, so they are coherent to each other. What is the meaning of coherency in a memory subsystem? It means that the concurrent execution should behave like the one by an atomic memory. More technically, for any possible memory request response sequence by the memory subsystem, if the system is correct, the sequence should be able to be simulated by the atomic memory as well. Let's look into more about cache coherence protocols. Each line in a cache consists of its address, value, and status. Here are some example statuses. M stands for modified, and it means that the line is both readable and writable. Another status is the S, standing for shared, and it means that the line is only readable. We also have status I, meaning that the line is neither readable nor writable. An important fact in designing a cache coherence protocol is that the coherence of a line is also known to coherence of others. It means that, in terms of correctness, it is fine to reason about the correctness for a single line first, and later naturally extend it for multiple lines. Now I'd like to provide an example to explain why designing a cache coherence protocol is hard. In this example, we have three caches, a parent P and two children C1 and C2, where the line statuses are all S. Suppose a scenario. The system wants to deal with two store requests, one to C1 and the other to C2. When C1 handles the blue store request, it does not have enough permission to write the value, since the status is S. In this case, it makes a request to the parent P with the RQM message presented here to get the M status. At the same time, it changes its status to a so-called transient state SM to record its current status S and the next expected status M. There is another purpose for transient states, which is not to allow any further external requests to C1. In that sense, we can also say that the transient state also functions as a lock. When the parent P receives RQM from C1, it needs to change the statuses of itself and C2 to I, so C1 can write the value with the M status while the others cannot access the value. So it makes another request to C2 called an invalidation request named RQI in this figure to change the status of C2 to I first. At that time, P also changes its status to a transient state as D to record its current status S and that it is in the middle of invalidation. We have so far only dealt with the blue request. However, there is a possibility that the red request is handled in the middle of processing the blue one. Thus, two transactions are now interleaved. Let's say that C2 started to handle the red request, also a store request. In the same sense, C2 changes its status to SM and sends RQM to P. A transient state of P here is very crucial to maintain coherence because it cannot handle the red RQM because of its transient state. If P were able to handle the red RQM, then it might lead to an incoherent state where C1 and C2 both have the M status. So the only possible next scenario is C2 to handle the invalidation request RQI and to respond with RSI to the parent. There is a subtlety in using transient states here. We see that C2 currently has the transient state IM, but it still should be able to handle the request RQI from the parent. What we learn about this example is that the use of transient states and the network topology, tree in this example, are very crucial to make interleavings correct. Then how do we formally reason about such interleavings? There have been a lot of attempts. Model checkers have used non-interference lemmas to ensure that interleavings are safe. However, lemmas must be designed and proven per protocol, and it is hard to be sure if the lemmas are effective enough. This work can be considered as how we reason about interleavings efficiently using a theorem prover. Generally speaking, we see that the biggest advantage of using a theorem prover is that we can state a general theorem with rich logic, prove the theorem once, and apply it multiple times. Applying this philosophy to verification of cache-coherence protocols, we first would like to formalize the most general form of non-interference, find abstract conditions that imply non-interference, prove this implication once, and use this theorem repeatedly for various protocols. With this motivation in mind, we have developed a framework called Hemiola, embedded in the CAV proof assistant to design, prove, and synthesize cache-coherence protocols. The framework provides a domain-specific language to describe protocols more easily, where any expressible protocol satisfies the most general non-interference called serializability. It also provides a novel invariant proof method that only requires considering execution histories without any interleavings. Finally, the framework provides a compilation and synthesis toolchain to run Hemiola protocols on FPGAs. Let me first introduce the Hemiola DSL. A system is the highest level component consisting of caches and message channels. There is a cache containing its local state and rules. A rule is a unit to make state transition steps. It takes input messages from some message channels, checks its precondition, makes a cache state transition, and produces output messages in queue to some channels. One very important concept in Hemiola is how the DSL deals with these transient states. Let's use an example where an L1 cache receives a write request, but just has the S status. In a conventional protocol description, we should check if the cache is in transition, set the proper transient state, and make an output RQN. Using the Hemiola DSL, we can just send a message RQN with no in-transition checks and no explicit transient states. Instead, Hemiola provides an abstract locking mechanism called uplocks and downlocks. We view a transient state decomposed into a stable status and a particular lock. For example, we can view this transient state SM as stable status S and uplock. A good thing about the DSL is that the locks are automatically set by using the Hemiola rule templates. In this example, we can use the RQUU, standing for request up template, and it implicitly checks and sets an uplock. The Hemiola DSL enforces a user to use the rule templates for every rule description. The templates are designed very carefully to cover practical request and response patterns. What is the benefit of using such rule templates? In terms of verification, any expressive protocol described in the Hemiola DSL satisfies the serializability property. And we define a system as is serializable if and only if, for any interleaved history, there is a legal sequential history that reaches the same state. Let me give an example to illustrate more about this benefit. This is the example we've just seen a few minutes ago, where the blue and red transactions are interleaved. Below, we see a legal sequential history where the two transactions are serialized. The serializability guarantees that for any interleaved transactions, there is a sequential history that reaches the same state. The biggest contribution of the Hemiola framework is that any protocol defined in this framework satisfies serializability by construction. Here, the on-tree predicate says that the system S should be defined on a tree topology. Also, good rules says that every rule should be defined by the rule template. Now, how do we make use of serializability to verify cache coherence protocols? Hemiola also provides a novel way to prove invariance on top of serializability by using so-called predicate messages, stating invariance based on the existence of a message. Revisiting the blue serialized transaction, when C2 receives RQI from the parent P, it changes its status to I. So we can have a predicate message for the response RSI claiming that the status of C2 is I. Similarly, when P receives RSI and responds with RSM, it changes its status to I. Using the predicate message for RSI and P's status change, now we can have the predicate message for RSM claiming that both P and C2 are invalid. We'd like to emphasize here that we could claim predicate messages so easily since there were no interference by the other transactions. Suppose that C2 is about to handle another red RSM presented in this figure. By such an interference, in this case, the predicate message for RSM becomes broken. On top of the Hemiola framework, we designed and proved hierarchical MSI and MESI cache-coherence protocols. The designs and correctness proofs take system topology as a parameter. An example here defines a topology where there are 4 L1 caches, 2 L2 caches, 1 last level cache, and the main memory. Every protocol designed in Hemiola can be compiled to the corresponding CAMI hardware implementation. CAMI is a hardware verification framework built in CAV, equipped with its own HDL and proof automation tools. The HDL is also rule-based, thus compilation is natural. The framework has a hardware synthesis toolchain, so we can put a Hemiola protocol to FPGA. In order to claim that the protocols designed in Hemiola are practical and competitive, we evaluated our case study protocols with an existing BlueSpec implementation. For this evaluation, we used the BlueSpec simulator, and we designed 4 artificial workloads that make random requests but mimic temporal and spatial locality of memory accesses. We measure the performance by counting the number of transactions performed in a 0.5 million simulation cycles. The result shows that the Hemiola protocols are competitive with a practical implementation coded by hand. We also synthesize our case study protocols to run in FPGA. On FPGA, we perform tandem verification covering over 1 billion memory requests for each protocol with a random workload and a reference memory to check its correctness. To conclude, we built the Hemiola framework where its DSL allows a user to design cache-coherence protocols and to prove invariance much easily by using predicate messages with the serializability guarantee. We designed and proved various hierarchical protocols on top of the framework and demonstrated that Hemiola indeed eases the design and proof. Please visit our GitHub repository for the framework, compiler, and case studies. Thank you very much for listening.